All right, welcome to the last part of Chapter 8, and we are going to talk about different ways that heat is transferred to and from materials in the real world. Finally, we're in the real world. And then I'm actually going to go back to the beginning of the chapter, and I'm going to talk specifically about thermal properties of gases and kind of how ideal gases work. And so this will finish us out for Chapter 12. And this is going to be heat transfer and thermal properties of gases. All right, and so halfway through the lecture, I will actually transition to a pretty separate idea, which is the thermal property of gases. So just be prepared and be on the lookout for that. All right, I'd like you in your notes to go ahead and draw this table, and I will be checking for this table on Monday when you come to class, and I'll make sure that you have it filled out. And that's the way that I know that you listen to this lecture. All right, so we're going to talk about methods of heat transfer, and there are three methods. There's conduction, convection, and radiation, and you might remember these from high school or middle school at some point. What I want you to do is go ahead and draw this table, and I want you to find in your book the definition, an example, and a formula, or any relevant constants that relate to these. Go ahead and pause the video and do that, and I'm going to continue along. So conduction is when heat is transferred between two objects because they are touching, right? Like your hands on a warm glass of coffee, or you sitting on a rock, and we'll actually solve a problem here later. Whenever you go out into the wilderness, it is actually really dangerous, or could be, to sit on rocks because they really just kind of suck the heat right out of you. You can get really cold really fast sitting on rocks. Or heat flow between warm and cold things that you might come into contact with. We do have a formula that's related to that. This Q over delta T is the rate of heat transfer between these two objects. The K is a conductivity constant, which you can find in a table on page 392, and I'll show it to you a little bit later. A is the area of that object, the surface area that's in contact with it. So if it's your rear end on a rock, then you have to kind of figure out, okay, well, what's the surface area of a rear end? L is like the thickness of the layer that is conducting it. And then delta T is the temperature difference between the two things that are touching. Right? So if my hands are at 33 degrees Celsius and my cup of coffee is at 70 degrees Celsius, then I'm looking at a temperature difference of about 47 degrees Celsius or 37 degrees Celsius. Convection is heat transfer between fluids, and so this could be a solid in a fluid, right? Like when you get in a pool, if you don't swim around or anything, you can get pretty cold pretty fast because water is not usually in 98.6 in a pool, and it just draws heat right away from your body. Part of why water is so very dangerous is it sucks the heat right out of you. Likewise, if you don't have a good insulating layer and you sit in a jacuzzi, the jacuzzi is warmer than you are. Heat flows from hot to cold. And so that jacuzzi will actually transfer heat to you, which would be the cold one in this case. And you can get overheated pretty fast in a jacuzzi, so jacuzzis usually have time limits on them for that reason. And then the last example of heat transfer is going to be radiation. And you can think of this as like heat through the atmosphere, right? It goes in waves. And so the heat that we get from the sun is a really good example of radiant heat. The heat that you get from like a bathroom heater is also a good example of radiant heat. I always describe this to my students as like the feeling of warm. and it's usually transmitted by the air through these kind of heat waves, right? And so in the summertime, you can actually see radiant heat coming off of the road or coming off of a car, and in the wintertime, you can see radiant heat coming off of people in the form of steam, especially if somebody has been exercising and they've generated a lot of internal heat. This one is full of equations, and so the prominent equation in your book is actually a simplified version of this, and it just says T right here, and that's probably what you wrote down if you pause the video. But I'm sorry, it actually says T to the 4th power. I want to expand on this and say that we're going to do a delta T, and so usually you get radiant heat loss from you standing outside or an animal being outside. And so I'm going to do this as your skin temperature to the 4th power minus the environmental temperature to the 4th power. And that way you'll get your problems right every single time. And so this is my preferred formula for heat radiation or heat loss due to radiation. Just do the temperature of the warm thing or the thing that's losing the heat minus the environmental temperature where that heat is being lost to. This fancy little E is the emissivity of the substance, and it differs for every substance, but your book has this kind of implied value. We usually talk about animals losing heat due to radiation, and so the emissivity of skin is 0.97. There's also another constant in there, and that's the Stefan Boltzmann constant, and that'll be the same every time. And so ultimately what you're looking at is these two values are the same every time, the area of whatever's being affected, and then the temperatures, and you'll get the rate of heat loss in watts. And remember, a watt is a joule per second. Same up here. This rate of heat loss is in watts, but 1 watt is the same as saying 1 joule every second. All right, so there's these big 3 ways that heat is lost. And we're going to do a couple of mathematical examples now that we can really only do math with radiation and with conduction. And so when you're presented with a problem, you need to decide, okay, are these 2 objects touching? And if so, okay, I use the conduction formula. Or is this heat being lost to the atmosphere? In which case, okay, then I use the radiation formula. All right, so let's do our first example. We've got Sally, who is at a body temperature of 37 degrees, pretty normal, and she's sitting on a cold granite rock at 0 degrees Celsius. 0 degrees Celsius is about 32 Fahrenheit, so we're looking at a literally freezing cold. She's out in some pretty cold weather. So up front, we should expect her to burn a lot of energy doing this. What is the rate of heat transfer and in what direction? So let's answer that direction first. We know that heat flows from hot to cold, so heat is going to be going from Sally to the rock, right? And then let's find out the rate at which that heat is transferred. So Sally's sitting on the rock, which means she's touching it, and to me that indicates that I've got a conduction going on, so I'm going to use the conduction formula, and I need the conductivity value of Sally. She is losing heat through her rear end, and that is going to be fat, right, at 0.21. I need to estimate the size of a rear end, so I am going to say that her legs are like 40 centimeters long, her rear is like 30 centimeters wide, and so that'll be our area, right? And I'm going to say that her fat layer, most people's fat layer is about 1 centimeter thick. And so L in our formula is going to be 0.01. And that's going to be the thickness of the layer that is losing heat. All right, and so we're ready to set it up. And we're going to say that Q over delta T is equal to the emissivity, the conductivity constant of fat, which is 0.21. Times the estimated area of Sally's legs / rear end. There we go. And all over the thickness of that layer, 0.01, and times delta T. And because it's a delta T, I don't have to convert the Celsius to Kelvin. I can just leave it as Celsius, and so the difference between those is 37 minus 0, which is just plain old 37 degrees Celsius, right? Or Kelvin if you want to do that. And so what I do is I do this first part and then multiply by 37. Take a second and do that, and I get a rate of heat loss at 93.24 watts, or that's the same as saying she's losing that many joules of energy every second. And so you can actually get pretty cold pretty fast sitting on rocks. So if you're ever outdoors, be really careful about this. You'll get the heat sucked out of you before you know it and get real cold. All right, so now we've got Sally, who has sat on this rock. And she's cooled down a little bit. Now she's at 35 degrees Celsius. And she's sitting on this rock. Or no, I'm sorry, she got tired of sitting on the rock and now she's standing up. But it's still really cold outside. And so what's her rate of heat loss now? Well, Sally's not in contact with anything, so this is going to be a radiant heat loss formula. Remember, I'm going to do Sally's temperature minus the environmental temperature. These two things are constants. And I just need to estimate the area of skin. In your book, it gives you the actual estimated area of skin is about 1.8 cubic meters, which is kind of a gross and disturbing estimate of how people might know that. But anyways, the emissivity of skin is 0.97, and the Stefan Boltzmann constant. Right now, all I really have to do is take those numbers and plug them in. So I get Q over delta T, her heat loss rate, is going to be equal to her emissivity, there we go, times the Stefan Boltzmann constant, e to the negative 8th, all right, surface area of skin, all right, and then her temperature, which is 35 degrees Celsius. Now this isn't just a temperature difference, right, and so I actually need to convert 35 to Kelvin. So I'll do 35 plus 273 gives me a temperature in Kelvin of 308, right? Equals her temperature. And then the outside temperature is going to be 0 degrees Celsius, which when I do that, 0 plus 273 is just 273 Kelvin. So I'll plug those in. I'll do 308 to the 4th power minus 273 to the 4th power. And when I evaluate, I'm going to do parentheses first, and then I'll go through and do the rest of the multiplication. So pause the video, go ahead and take a second and do that. And after I take care of that order of operations, I get 341 watts, or 341 joules per second. And then if I want to think about that as kilocalories per second, then I can convert joules to calories. And, there's 4.2 joules per 1 calorie. And then there's 1,000 calories per kilocalorie, big C. And after I do that division, I find that she is burning about 0.08 big calories, kilocalories per second, which if I multiply that by 60, puts her at burning about 4 calories every minute, right, just from standing outside. And so when I told you guys the other day in class that you actually burn more calories in colder weather, well, this is why, because your body is struggling to maintain its internal temperature. All right. So now we're going to switch modes and we're going to talk about thermal properties of ideal gases. These are also known as the ideal gas laws, and if you ever take chemistry, you'll see these there as well. An ideal gas is just that. It's a gas that acts the way it should. Gases, however, are made of chemicals, right? Things that come from the periodic table. And we already talked about in the last lecture that gases have a really high kinetic energy. They tend to fly around, and chemically speaking, when things have a high kinetic energy, and fly around, they run into each other, and that causes chemical reactions. And so we're going to assume that none of that happens, and we're just going to talk about the energy of a gas. All right. While this is a really simplified model, it's also pretty applicable because, well, it is simplified, and yes, chemical reactions happen, but gases in the real world still behave this way, and you're pretty familiar with that. And so in the email that I sent you, oh, not yet, sorry. So we're going to explore this idea of pressure for gases. In daily life, pressure is a lot like a force, and you might think of it like a force. It's a push, though, on the outer surface of something due to the forces of those molecules flying around. Be it your skin or a basketball or a water balloon, there are things, right, pushing against some area that cause you to experience pressure. And even sitting wherever you're at right now, you've got pressure pushing on you. You're just so used to it, you're not aware of it, and that's atmospheric pressure. And so whenever you drive in the mountains and you go up, 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 or if you fly on a plane, that atmospheric pressure decreases, and you feel that in your ears and in your sinus. And then as you go back down, pressure increases and your ears get happy again. Right? Ears are a pretty good gauge of pressure. We've got this generic pressure formula that pressure is equal to force over area, and we'll talk about that in a second. This is newtons over square meters, and this is a compound unit that we're going to call the Pascal. And so when we talk about absolute pressure, we are talking about pressure in pascals. I want to ask you, though, not going up, what happens to pressure as the area over which a force is applied gets smaller? And to do that, we are going to explore Chinese massage and stilettos. So let's imagine that we've got, somebody getting a massage where their back is walked on. What force is being applied on that person? Well, the force is coming down through either foot, right? And if this person lifts up one foot, then their entire weight force is pressing down on one foot. So that's what we're going to explore. The force is going to be equal to the mass of that person times gravity. You guys know that I love to use 70 for the mass of a person. Oh, there we go. Times gravity, which is 9.8. And we get a force of 686 newtons. And then I'm going to estimate the area of a foot. For this particular one, I'll say, I don't know if it's like 10 centimeters by maybe 25 centimeters. That's about how long a foot is. Sure, and 10 centimeters is about how wide. And so that gives us an area of 0.025 square meters, right, for the area of a foot. And so all I'll do is just take this force of the person divided by the area of 1 foot. We'll imagine they're standing on 1 foot. 0.025 square meters. And we find that this applies a force of 27,440 newtons per meter squared, or pascals, right? But then let's say we put our massage therapist in stilettos, and we halve this area, right? We've still got the same force. It's still 686 newtons on this person, but we halve the area down to 0.0125, because not a whole person's foot is pressing down a stiletto. There's this little tiny front part, and there's this little tiny back part. And so what's going to happen to that overall pressure? Well, when you do that division, you'll find that the overall pressure goes up as area goes down, and so we wind up with 54,880 pascals. And so if you ever go get a massage like this, do not let them wear stilettos. Way more pressure that way. Pressure also works in gases. So we just explored force, right, from a person. However, these little gas molecules, they carry a mass, and they do have a velocity. And so ultimately what we find is that these little gas molecules can apply a force based on whatever's containing them. You probably know this in your tires, right? And so if you've ever suffered a flat tire, you have to go to the gas station and pump more gas into that. That gives you more molecules that are flying around inside. And those molecules tend to bump up against the walls of your tire. And as they do, we say that you've increased the pressure and now you've got a nice happy tire as you add more molecules of gas, right, within that same volume. Same idea in a balloon. As you huff and puff, it's actually the collisions of all those little tiny gas molecules with the outer surface of the balloon that give it its rigidity. Or its shape. Now balloons are a little bit elastic, and so their volume actually increases as you increase the number of gas molecules because the pressure increases, right, as you increase the number of molecules in there. And then if you were to take a pin, all of those gas molecules would suddenly be released into the atmosphere, no longer confined to the balloon, and the pressure would go down and you'd have a very sad balloon, right? It would deflate and it would not have enough pressure to be a balloon anymore. All right. Pressure is a funny thing, and it is measured, I told you, only in pascals, PA. However, it's not only measured in pascals, and it really kind of depends on the situation. So when we talk about tires, we measure pressure in PSI. We also do this in SCUBA, and this stands for pounds per square inch. Per inch squared. And then when weathermen talk about pressure, they talk about atmospheric pressure because, well, that's what they're talking about. In physics, we are always wanting to get to the Pascal. And so we're going to have to take the situation that we're talking about, and we will have to convert it to pascals. And so down here, you've got your conversion factor for that. And let's say that I am diving. And we'll do a little problem right now. Let's say that I'm diving and I'm down at about 10 meters deep, and so I don't know, maybe like 30 feet. That's pretty much what 10 meters is. At 10 meters, I experience twice the pressure that I do at sea level, which is 1 atmosphere. Right? As you go up in elevation, you get less pressure. As you go down in elevation, you get more pressure, and so as you go into the sea, you get even more. So at 30 feet down diving, I experience 2 atmospheres of pressure. We're going to convert this to pounds per square inch first, just to give you an idea of what that is. And so I know that for 1 atmosphere of pressure, there are 14.7 psi. Right? And when I convert that, I find that I've got 29.4 pounds per square inch pressing down on me at 30 feet of diving. And then if I wanted to take that number and convert it to pascals instead, because that's what we're going to be using in physics, then I know that, okay, well, I've still got the 2 atmospheres of pressure, except this time I'm trying to get to pascals. And so I know that 1 atmosphere is equal to 101,300 pascals, PA. And so I get a final pressure. I need some room to write that. I get a final pressure of 202,600 pascals of pressure, and then I can start using the formulas that I'll be using. And so when I talk about pressure, we represent that with the variable P, and when I do that in physics, I'm talking about pascals always. So just be careful in problems. If they're giving you atmospheres or if they're giving you PSI, you do have to do a conversion. Just like if you're given centimeters, you've got to convert to meters, and if you're given grams, you've got to convert to kilograms. All right. Gases have this other funny little number that we talk about. Gases are not confined to a specific volume or shape. They take the shape of their container. And there can be lots and lots of atoms of gases depending on how we confine them. And so we don't talk about number of atoms of gases really. We talk about gases in terms of this thing called a mole. And again, if you've taken chemistry, ever, then you know that a mole is just like a chunk. And this chunk, if you're interested, right, is this many particles of gas, right? And so if I have a monatomic gas, like neon or argon or any of the noble gases, then I'm talking about this many atoms of gas, right, in 1 mole. But typically we talk about lots of moles of gas. In a formula, this is represented by the variable n, and so you can just think of it in physics as chunks of gas, right? I've got 1 mole, I've got 2 moles, I've got 3 moles of gas, and as the number of moles increases, so does the number of atoms that I'm kind of pumping in to that, and each one has this huge number, 6.02 e to the 23rd molecules of gas in it. All right, and this is actually known as Avogadro's number. G-A-D-R-O. And so again, if you've taken chemistry, you're very familiar with Avogadro's number. I'm not going to make you guys figure out moles, just know that it's a chunk of gas, and the more you have, the more atoms you have. And so in your email, I sent you a link to this little Java applet, and what we're going to do is we're going to use this applet to talk about ideal gases. And so it's got a little bicycle pump that you can pump atoms of gas in there. It's got a little pressure gauge and a temperature gauge that reads in Kelvin, and this little guy that can kind of change the volume of this container that we've contained that gas in. We're going to talk about what happens to these atoms as the temperature goes up, what happens to these atoms as the temperature goes down, what does that mean for pressure, and what happens as I increase and decrease the volume of this. And so if you want to take a second, check your email, open that applet, you're welcome to do that. But if not, you can just watch me do that. And so we'll answer these in this order. We'll play with the temperature and kind of see what happens. And we will play with the volume and kind of see what happens. And so this is how thermal energy is related to pressure and gases. All right, so I am going to introduce, let's say we'll do 1 mole of gas in there, and I'm going to let these disperse and just act like a normal gas should. Right, these have a high kinetic energy, they're kind of randomly bouncing around, and it is their bouncing on the outside of that container that allows this whole thing to have pressure. Right now we're sitting at 0.36 atmospheres, which is a little bit below what you currently feel where you're sitting. And currently this whole thing is at 300 Kelvin. And so the first question that I asked you was what happens to these molecules as I add heat? And so what I want you to watch is the kinetic energy of the molecules and the pressure of the molecules. And so as I add heat, these begin to move a little bit faster. The temperature goes up because of that kinetic energy, and the pressure goes up as well. All right, I'm going to let these calm down just a second and watch that pressure go up, up, up. And if I keep letting it go up, they'll move faster and faster and faster. The temperature will get higher and higher. And ultimately what I'll find is that I'm actually, going to break this container. All containers have a physical limit. All right? So let's return the lid and let's start over. Let's get a little bit of gas going in there. Ooh, a little bit more than that. There we go. I'll let them start acting like normal. Again, we're at 300 Kelvin. Our pressure is going to build up as these things collide with the walls. But instead of adding heat this time, I'm going to remove heat and go ahead and make a guess. When I added heat, they moved faster and the pressure went up. So what do you think is going to happen when I cool them down? All right, and when I cool them down, the temperature goes down. That makes sense. Kinetic energy lowers. And, my pressure goes down significantly. If I do this with real objects, sometimes instead of this container kind of blowing open, what we see is that they tend to crumple. Right? And so I'm gonna speed these back up one more time and get them moving. Come on, little atoms. All right, there we go. I'm gonna get us back up to a reasonable pressure. And then our other question is, well, what happens to these things as the volume increases? And what happens to these things as the volume decreases? So I'm gonna give us a little bit more gas so we can kind of see that. There we go. And I'm going to heat them up just a little bit and get us up to about 300 Kelvin. All right. A little bit more. All right, a little too much. What we'll see is that as I change the volume of this, as I decrease the volume, what do you think is going to happen to the motion of the gas? Well, they've got less space to move. Collisions happen with the wall more often. And so as I decrease the volume, the temperature tends to go up. And as these collisions increase, the pressure goes up too. Right? And so what we're starting to see is that temperature and pressure go hand in hand. As temperature goes up, pressure goes up. And as volume decreases, both of these things go up. So that's an inverse relationship. But then if I open it back up and I increase the volume, the inverse happens, right? As volume increases, then temperature goes down and pressure goes down. Right? And so when we come back to what we were talking about, right, we see that as temperature goes up, so does kinetic energy, and thus pressure and temperature. And as temperature goes down, then pressure goes down. But volume has this inverse relationship. As volume increases, pressure decreases, as does temperature. And as volume decreases, will pressure and temperature go up. Right? In this app, you can also talk about constant volume processes. And so in this app, well, what happens if I keep the volume constant and I change all of these other things? So, I don't know. Let's try that. We've got things moving as normal. I'm going to go over here and check constant volume. Right? So I can't move my little guy back and forth. That's not going to work. But what happens when I add heat? All right, well, the pressure goes up pretty quick, and so does the temperature. And if I remove heat, well, then just the kinetic energy of that decreases. Right? I can do the same thing for temperature. If I keep temperature constant, but I change the, if I change the volume, what we find is that the kinetic energy has kind of a hard time. So we don't see too many isothermal properties happening. And then I can keep the pressure the same as well. And that's going to allow temperature and volume to change. And so what you're going to see is this little guy moves back and forth automatically. I'm going to try and increase the temperature to increase the pressure. Oh, temperature goes up. Guy has to back up. All right, and then I'll remove it. Temperature's going to go down either way. And then this guy's going to have to decrease the volume to keep the same pressure within that container. All right? So you can play with this little applet. It's pretty good at helping you kind of learn that content. We can have these constant volume processes, or we can have these constant temperature processes. But either way, what we see is that these things really tend to go together. So pressure and temperature are closely related, and volume is inversely related to these things. And this leads us to an equation, right, which is our ideal gas law. We say that the absolute pressure of a gas in a container in pascals is directly related to the volume in cubic meters. N is the number of moles, or the number of, remember, we are going to call these chunks of atoms of gas. And so these are equal to the number of chunks. R is a gas constant, right? And it'll be 8.31 every single time. And then the temperature of that gas in Kelvin, right? And so I'm going to take this time and do a little example with you. All right, so what we see is that as we change the temperature, kind of like with energy and momentum, we have these before situations and we've got these after situations. And so I can change the temperature, and if I do that, then, well, other things about that ideal gas change as well. And so we can think about this as the final version and the initial version. Doesn't matter what you put where, but things change proportionally to one another. And what we see is that pressure and temperature are intimately related, and volume is an inverse relationship with both of those. We do have a little bit of vocabulary. We've got constant volume processes, which are where the final volume is equal to the initial volume. A good example of a constant volume process is like your tires, right? And so when we cool your tires off in the wintertime, what we see is that your pressure decreases from that because that volume is constant. So as temperature decreases, overall your pressure decreases in the wintertime. There are what we call isobaric processes, which are things that have a constant pressure. Divers have these things called isobaric chambers. And so if a diver does a few things wrong and kind of gets sick and changes their pressure too fast, they have to go to an isobaric chamber where the pressure is kept constant and their body can recover. And then there are these things called isothermal processes, where there is this constant temperature, but the volume and the pressure can change. And a really good example of an isothermal process is your lungs. Right? And so when we look at this whole initial and final situation thing, if we have a constant volume process, then we don't need to worry about that part of the equation. If we have an isobaric process, then we don't need to worry about this part of the equation. And if we have an isothermal process, well, we don't need to worry about this part of the equation, right? Because they would be equal on either side. And so as you use this formula, just be careful and try and recognize, okay, is this going to be a constant volume situation? Is this going to be a constant temperature situation? Or is this going to be a constant pressure situation? Or it could be none of them. And if it's none of them, right, and everything can change, then you use the whole shebang. So let's try an example. Let's imagine that I have a container of ideal gas and it's at 1 atmosphere of pressure. All right. We're going to assume that the container itself is constant. And so in my mind, that triggers, okay, the final volume is going to be the same as the initial volume. So this is a constant volume problem. By how much would the sample need to be heated to double the pressure? Right? And so I've got this before situation and this after situation. I know that pressure initially and temperature initially are going to have to equal the final pressure and the initial, or I'm sorry, and the final temperature. And I'm saying, okay, well, I know this, and I can kind of assume this, and I know that I've got to double the pressure at the end. So I'm going to take 1 atmosphere and convert it to our SI unit, which is pascals. And so for this initial situation, I'll say I'm at 101,300 pascals. And we can say we're at an initial temperature of, I don't know, 1 Kelvin. That's fine. And then I'm going to set that equal to, well, I know I've got to double the pressure in the last one, right? And so my final pressure is going to have to be double my initial pressure. So you can go ahead and take that initial pressure and multiply it by 2. It's going to have to be 202,600 pascals is the pressure I'm looking for. And then, well, how much am I going to have to change the temperature? Well, I don't know how many Kelvin that final temperature is going to be. You can do this one of 2 ways. You can cross multiply, right, and do 202,000, right, and then equals 101,300 times x, or you can just say, well, I know I've got to multiply by 2 to get there, so if this is a proportion, then I'm going to have to multiply by 2 to get here. My new temperature is going to be 2 Kelvin, will take me to twice the pressure. By how much will it need to be heated? Well, the temperature will need to double. Right? Depending on what temperature I start at, I'll always have to double it. Right? What we see is that as I change the temperature of a sealed container for an ideal gas, this can actually do work. And this is the whole idea behind a piston, right? The very thing that makes your engines work. If the volume changes, well, then I've got a force times a distance, which I can talk about as a pressure times a volume, and that'll give me my work done. So in this case, if I have a change in pressure, or if this is, If I have a change in pressure, then it is the pressure times the volume, which as the pressure increases, then the volume will increase. And what I see is that I actually get work done. And so sitting in your engine of your car, right, if you're 6 cylinders, then you've got 6 pistons. And the heating of the gas within those causes the piston to go up and down. As the piston goes up and down, then it does work within your car that actually makes it move forward through a series of simple machines. All right, which brings us to your homework. Page 398, you have a couple of conceptuals. You've got some quantitatives there. And remember, this is all about heat transfer, which we talked about in the beginning. And then ideal gas processes, so gases. All right. And do you remember that table from the beginning of the lecture is how I know that you listened to it? So make sure you've got the definitions and the formulas. And on Monday, I will have a formula sheet for you for chapters 11 and 12 that you can start using on these homeworks. Happy studying!